Today we're going to talk about another form of concurrent programming called Shared-State Concurrency. This is the final one we're going to see in the course. It's the worst one. You can tell it's the worst because we have noise there. And but it's still used a lot in industry. Okay, so I'm going to explain that one. So let me give first introduction. We have seen three good ways of doing concurrent programming. In the beginning, we saw deterministic data flow. This is the best. It's completely deterministic like functional programming and it's concurrent. We also saw this in a previous course. But you cannot always do that. Sometimes you need non-determinism. And so then you can do multi-agent programming. This one we saw a lot in this course with port objects. And we also saw a lot about an industrial language that uses this paradigm called Erlang. So this is a nice paradigm. And then the best one in my view, which is not supported by any language so far, is deterministic data flow most of the time, but you add ports or agents in small amount, only where you need it. So this is the best one, by far, but no language supports it yet, maybe someday. Okay. Today we will see a fourth paradigm, which is in fact the worst of all of them, the hardest to program, but it's used a lot. This is called Shared-State Concurrency. This is what happens when you have threads and cells together. Okay. Cells and threads together are somehow very hard. It's much harder than multi-agent where you have ports and cells together. Okay. So we're going to see how to use this. And in order to use this, you need to build abstractions. And we're going to see three important abstractions: locks, transactions, and monitors. Okay? The basic one is locks, building big atomic actions, and then built on top of that are transactions and monitors. Transactions are very important. They're used in database. They're very useful. So this is going to be a very important part. But monitors are, in my view, deprecated. You should never use them if you can avoid them. And never, if you make a new application, do not use them. So why am I teaching it to you? Because a huge amount of legacy code is using this. Still today, in Java this is called synchronized objects. So why is it used? Well, because when it was invented, people thought it was useful, okay? And in those days, it was and so languages built this in, but it turns out this is very hard to use. But still, I'm going to teach you all about monitors, okay? So locks and transactions are good, but monitors are not so good. So that's the short summary. To introduce the paradigm, I want to refresh your memory on cells very quickly, because the whole thing is based on cells. Okay. Mutable state. We saw this before. I'm just going to refresh your memory quickly. Variables that you can assign multiple times, and we call it cell, because I don't want to use the word variable. Okay. The word variable has a huge number of meanings. In mathematics, you have variables in equations, but they're actually constants in the equation. They don't vary, except you can have different forms of the equation. In computing, a variable can be either an identifier, or something in memory, or a cell. So, I don't like to use variable, the word variable, because it's a confusing word. So I use the word cell. Okay, we saw this already. A cell is a box with a name. The box has a name and a content. So this is like addresses in memory. A memory, part of memory, it has an address and then the content. When you have a pointer in a language with pointers like C, so the identity is like the address, and the content is what's stored there. So this is the idea, and we make semantics of this. So I'm going to refresh your memory very quickly on this. It's a very simple thing, in fact. We add 3 operations: creation of a cell, a new cell C with initial content A. We can do an assignment, replacing the content, and we can access the content, okay, using this read operation. In many languages, the read operation is implicit. If you do something like x equals y plus z in C or Java, these are actually going to do access automatically, yeah? And this is the assignment. But languages, they like this because it looks like a mathematical equation, even though it's not, because these are all cells, okay? And this is an assignment, and here you're accessing the value. So on the right-hand side of the equal, these will be implicit. But I don't like that because it's confusing, in fact. You have to understand it. So here, the access will always be explicit. If you don't do this, use this @ sign, you will not read the content. You will get the address, the name of the cell, which is a constant. So it's like a pointer. You can see of a cell also kind of like a pointer. So we saw this already. It's just a refresher, and we saw operations you can do. So here you have a cell X with content 0. I can write it like this in a box. You can have aliasing. Aliasing happens when you have 2 names to the cell. So you can have actually 2 identifiers referring to the same cell. And in a language like Java, you could have 2 variables with the same pointer inside. So this is called aliasing because they are actually referring to the same thing. So if you've assigned one of them, like y, x is of course changing too. X also changes. So that's something you can do with cells, and that's how to use them. Okay, and then we made a semantics. So very simple refresher. You can formalize this very simply. You have 2 stores, sigma1, which is the regular variables. So these are actual mathematical variables, single assignment, they have 1 value. Then you have the cell store, and a cell is a pair in the semantics. So sigma1 is variables with their content, like x, which is here, it's equal to some weird content called c, or t is equal to 10, or whatever. Z is an unbound variable. And here, in sigma2, you have pairs. So a cell is a pair. So the first part of the pair is the name of the cell, and the second is the content. So you can see that it's not actually a variable. It's more complicated than a variable, a cell, because you can assign it. In the semantics, this is more complicated than just a variable, because when you assign it, you can change the second part, and the first part always stays the same. Okay, so the name of x, which is a cell, is a constant, and here I'm putting in a constant c. So these are unforgeable, unique constants that determine the name of the cell in the semantics. You can consider it to be like the address. But here it's more abstract. I don't want to assume any kind of memory architecture, so I'm just making it an abstract constant. And here you have zeta, so you have 2 of them, 2 cells. And the content of x is t, the content of y is w. And if you do an assignment, you will change the second part of the pair, and not the first one. So semantically, that's what's happening in a cell. So you can see a cell is a more complicated thing than a variable. A variable is just a name for a constant, in fact. You call it variable, but it's actually a constant. So that's why, the word variable is used in mathematics, because when you have an equation, you can instantiate the variable to many different possible values. But for each use of the equation, it's a constant. So that's what it is semantically. So you can see it's a little bit more complicated than a regular variable. Okay, but now I want to do something new. Now we're using we're doing concurrency today. Concurrency is very important. And for concurrency, we add a 4th operation. I mentioned it before, but now I will really emphasize this one because this is really very important operation called exchange. This is an operation with two arguments, whereas read and write only have one argument. You read or you write x and y. The exchange has two. So exchange CXY is the same as doing a read and a write. And they're done atomically. That means the scheduler can never stop in the middle. It's all or nothing. It's single, indivisible action. That's really important for concurrency. The read and the write are done atomically. It turns out it's so important that even the processor architectures are going to support these instructions. Okay? We will implement our abstractions using exchange. When we do locks and transactions and monitors, we're going to use exchange to implement them. Okay? When we implement reentrant locks today, for example. It's possible to do it without exchange. In fact, theoretically, all you need is atomic read and atomic write, but it's much, much more complicated. If you want to see how complicated it is, go into Wikipedia and look for Decker's algorithm. Decker's algorithm is doing critical section with only read and write. It's really complicated thing. Oh, terrible. But if you have exchange, everything becomes simple. And it's so useful that even the processor hardware, the hardware architectures, all hardware architectures are supporting this kind of instruction. Of course, there's many variations, but you can see they have funny names like test and swap. So the test is actually a read, and the swap is doing a write. You're switching between a register and memory. Compare and swap, or test and set. Set is like a write, and the test is a read. Now you're comparing. They're all doing read and write. All processor architectures. This one here, which is an Intel Core i7, is doing it. The ARMs are doing it. All of them are doing it. Okay. Showing you how important it is. It's supported in hardware because otherwise things are much harder. Okay. So we're going to use exchange. So that's one thing. So that gives you a refresher on cells. And remember that exchange. Okay. And now I want to talk about how do we do shared state concurrency? Why is it hard? And how do we do it? And the way to do it is by building big atomic actions. Exchange is a very small atomic action, but usually you want bigger ones. Okay? So let me explain now, step by step. Shared state concurrency. So that's the paradigm we're looking at today. It's a programming paradigm in which you use threads and cells together in the same program. It's widely used, okay? And Java, C++, all older languages. Some of the newer ones are doing better. They are more multi-agent. Languages like Go. The current trend is to go toward more multi-agent languages. But many of the very popular languages are still doing this paradigm, okay? But it's, in some senses, a deprecated paradigm, as you will find out in the next 10 or 20 years. In fact, the use will be less and less, but it's still used a lot, okay? So it's the most difficult paradigm. That's funny, huh? It's so popular, and used to be almost the only one, but it's the hardest one. And you will see, and I will explain why. I want to explain you why it's hard. Why is using threads and cells in a program hard? And we can explain that in a very technical, in a very precise way. Why is it hard? Okay? Here is an example to show you why it's hard. I have two threads, and they are referencing cell C. So T1 and T2 reference C, and they do read and write. They might do exchange, but let's just look at read and write for this example. So the A0, A1, and B0, A1, they be either read or write operations on the cell. Okay? So T1 is doing n operations. Here I have 10, but in general, n operations. T2 is also doing n operations. Each thread does n operations. Now, of course, these threads are executing with the scheduler. And the scheduler will choose how to interleave these threads. That means the choice of these operations is kind of varying a lot. Maybe the first one is A0 if the scheduler chooses T1, or maybe it's B0. Then you do A0, maybe you do B0 and B1, and then the scheduler chooses A1, and then you do B2, and then you do A2, and so on. So the scheduler can actually choose. So there's a lot of variability, non-determinism there, because of the scheduler choices. My question now is, how many choices are there? In fact, if you have n operations on each, that makes a total of 2n operations. And they're like slots. Right? If you look at I have a little bit of space here. The scheduler will choose operations, and you have slots. If you have n operations, there's actually 2n slots. And you can choose an operation from T1, or you can choose an operation from T2. Okay? So there's many ways of choosing. I have n operations from T1 on 2n slots. So that's combinatorics. If you remember from combinatorics, choosing n slots out of 2n, so the order of the slots does not matter, just which slots you have, is the 2n choose n. N objects chosen out of 2n. And you can compute this is 2n factorial divided by n factorial squared. And once you choose the n slots for T1, the other slots, there's no more choice, okay? There are 2 operation instances in all. T1 picks n of them, and T2 gets the rest, which is also n. You can compute what this is. I recommend as an exercise. Here is a simple summary. Factorial, you can approximate it using Stirling's formula. So n over e to the power n times the square root of 2 pi n. That's very close to n factorial when n goes bigger. If you put that in here and you simplify, the whole thing is 2 to the power 2n divided by the square root of pi n. Okay? Notice this is exponential function in n. As n grows, this number grows exponentially. So the number of interleavings is exponential in the number of operations. Now the problem is all of those have to be correct. If one of those is buggy, then your program is buggy. And eventually, the scheduler, when you run it in real life, it will pick that one, and then you're dead, okay? And it will probably pick it at the worst possible time when you're in an airplane and you're landing or something, huh? Or you're in a hospital and something is operating on your heart and it's beaming radiation or something like that, huh? You never know. But all of them have to be correct. And there's an exponential number. How do we do that? That's not easy, okay? That's a lot. And you don't want to do them one by one, okay? You do not want to do them one by one. Okay, so summarizing, the number of interleavings is an exponential function of the number of operations. It's because you have cells and threads, huh? 2 threads with a shared cell. That automatically gives you this exponential function. If your program is correct, all interleavings must be correct. Okay? Even a small number of incorrect interleavings will break the system because, of course, this thing is going to run millions of times in any real program. Maybe it's a database, maybe it's inside of a car, maybe you bought a Tesla and it's running this software, okay? And then at some point, the Tesla, it brakes very hard on the highway because, I don't know, it thinks that there's an obstacle This is an actual real bug that is annoying Tesla owners, okay? I don't know if it's due to concurrency, but there might be concurrency bugs. They're hard to debug, okay? They're very hard to debug. You cannot rely on scheduler timing, of course. Come on, that's magical thinking, okay? You really have little control because this depends also on the environment. The whole thing is running in an environment, other things are happening, and the scheduler is trying to make things work in there. It's very non-deterministic, yeah? So even if you do like little delays, you're never guaranteed, okay? You can not, that's a real important rule. Never tweak the scheduler timing for correctness. You can tweak it for performance, okay, the scheduler time, but not for correctness, okay? Because it'll always break eventually. And you can do testing, and you can do verification, of course. Testing, you test, you know how to test. The problem is testing is very hard if you have an exponential number of interleavings. You cannot test all of them because the number of operations keeps growing with time. So it's really, really huge. You can only check a small fraction of them. But maybe you can do verification. Maybe you have a course, you've taken the course of Shared-State, where you do model checking. Wow, model checking, very miraculous tool. But model checking also does not handle exponentials very well, because it looks at all the possible execution states, but you can only do that for small programs, okay? You can find bugs, but you cannot prove correctness with model checking, okay? Except for small programs. So these two are useful, but they don't cut it for concurrent programs. There's only one way to make a correct concurrent program, is it has to be correct by design. That means that you have to think when you write it, and your design has to be correct. And then it's easy. And then if there's a bug, it's not a bug in the design, it's a bug in the implementation of the design, and that you can fix, okay? But if the design is correct, then you can make it correct. This is the only way to do concurrent programs correct by design. So that's what we're going to do today, okay? We want to design correct concurrent programs. This was always true for, this was also true for multi-agent and for deterministic data flow, of course, So designing concurrent programming means to manage the interleavings. You have exponential number of interleavings. What's the simplest way of managing it is to reduce the number of interleavings to a very small number. You can actually, in smart ways, you can reduce the number of interleavings. Okay? And here's three paradigms and how they do it. Deterministic data flow with ports isn't the best way, because it uses Church-Rosser. So deterministic data flow says all interleavings give the same result if you don't use ports. If you don't use ports, they all give the same result. So we don't care. That's the best solution. It works for all interleavings because the paradigm is designed, does that, okay? And if you add ports, like you do a client server, you only have a small number of ports. So for those, you have to check the interleavings. For example, if you have client server, the clients can send their commands in any order. So you have to make sure that it works no matter what order the clients send the result. Okay? That is much easier than checking all the program. That's the easiest. The second one is message passing. So multi-agent port objects, something like Erlang. And this is also much easier because internally, each port object has one thread inside. Or each Erlang process, there's one thread inside. And this thread will receive messages from the outside, and the messages are only handled in particular points. They're not randomly injected into the port object. They're only handled when the port object asks for the message. So the number of interleavings is very small. You have an internal state, which is consistent. A message arrives, when the port object wants it, and it computes a new state. So all you have to do is make sure that when the message arrives, you correctly compute a new state. You're done. Okay? This is very successful. Okay, this works very well. For each port object, you have one thread, and it only receives messages at certain times. So you have a lot of stuff going on, and then you have a message, and then a lot of stuff, and then another message. Okay? This is successful. So Erlang uses this, and it works very well. Today we're going to talk about this one. Atomic actions on shared cells. So now we have a shared cell between threads, many interleavings. What are we going to do? We're going to group the operations. So if you have operations, A0, A1, A2, A3, we're going to group them together so they're atomic. We're going to have operations to build big atomic actions. And this will reduce the number of interleavings. This is how transactions work, this is how monitors work, and it's all based on locks, which are the basic way of building big atomic actions. So the idea is to group operations together so you have big atomic actions. And if they're big enough, then it's a little bit like the port objects. Then all of these atomic actions are actually doing something useful, and then the scheduler can only choose the order of these big chunks. Okay, so you just have to make sure that after one of these big chunks that the data structure is consistent. Okay, so it's much easier. So this is how you do it for shared state concurrency. Okay, this is what we're going to talk about in the next couple of lectures. So the main technique is building large atomic actions. The basic concept is called the lock. A lock, a verrou, a lock. And you'll see why it's called a lock. Basically, it locks a piece of code so that only one thread can go inside at a time, and that makes it atomic, okay? And on top of the lock, you build monitors and transactions. A monitor and a transaction, they're just a lock with something else. All these three are actually locks. The lock is the basic one. It's building a big atomic action. But the monitor and the transaction, they add something more. The monitor adds this thing called the wait set so that threads can collaborate. This is for collaboration between different threads. And the transaction adds the ability to abort. So the transaction can correctly execute, but it can also abort, which means that the state is returned to the initial value. This is really important if you can have failure, if your disk crashes, or your network crashes, or whatever. When you pay on a bank thing, or using PayPal, or whatever, the payment is always a transaction. That means either you pay or you don't. There's nothing in between, okay? So this is very important, adding this ability to abort, okay? These are the three basic concepts, but all of them build on top of the lock. So we're going to first talk about locks, okay? In fact, you can see it as kind of a hierarchy. It starts with something which I call a simple lock. This is the most basic thing, but it's a little bit too simple, as you see. The practical one is called reentrant lock. So all of the locks you use in languages, like in synchronized objects that you will see in real languages, they're all going to be reentrant locks. That's the one that's actually used. But a simple lock is the simplest version of a lock, but it's a little bit too simple, as I tell you. So the real one that's used is a reentrant lock, okay? And then you can add something called a wait set, a way of threads of waiting for other threads. So a way of collaborating between threads, that gives you monitor. Or you can add the ability to abort. That's called a lightweight transaction. And then if you make it with stable storage, you have seen transactions in other courses, no? Have you seen transactions? Who has seen transactions already? No? Have you seen? No. Oh, great. Well, then that means this is the first time you will see transactions. A full transaction is built on a disk, a stable storage. And it has something called asset properties. It has 4 properties, A, C, I, D. D is for durability. It means persistence. It means even if your system crashes, the disk still has the data, okay? And when you reboot, the disk will let you recover. And the transaction takes advantage of that. So a full transaction will work even if you have real crashes, because it uses the disk. And this is the D. It's called durability or persistence. Persistence means it keeps the state even after a crash. Okay, so this is the main one. There's variations which I will talk about, but which you can see. There's different kinds of transactions, hierarchical transactions, sequence where you have things called sagas, whatever. There's all kinds of variations which I won't talk about. But this is the one that's really used in real databases. Okay? Monitors and transactions are just locks with something else added. Okay? So that's what we're going to talk about. This is the outline of the next 3 lectures, in fact. Today, I'm going to talk about this part, and next week we'll talk about monitors, and then we'll talk about transactions. Okay? And now I give you like a summary. How to prove. You have to reason. You have to do correct by design. We assume the program is only using atomic actions. Locks. You have locks everywhere. Grouping things. In fact, the locks will be on abstraction boundaries. So if you have a queue or a stack or dictionary, some kind of abstraction, then the abstraction will have a lock, will be inside of a lock. That means when you do the abstraction, you're guaranteed that it's correct even if it's concurrent. Okay? The correctness proof of the concurrent execution is very similar to the correctness of the abstractions themselves. If your queue is correct, putting a lock around it will make it work in a concurrent setting. So this actually makes things fairly simple. Okay? So the proof is actually 2 parts. One is that the atomic action is correct by itself. So this is actually proving that the abstraction is correct. This you already know how to do, I hope. Maybe you have something called an invariant that you know that it's correct. It's preserved by an atomic action. And then the next step is the sequence of atomic actions. So each one is preserving the invariant. That means everything's fine, but it has to make progress. It has to not turn around in circles, but the atomic actions have to actually make progress. So this is actually called liveness. Okay? Remember, we did the lift control system. You can do it in a similar way also for multi-agent. You want to prove there's a schedule. Remember, the lift has a schedule, which is a list of floors it has to go to. And you want to prove that the lift will always eventually go to the lift that is first in the schedule, and it will correctly update the schedule. So remove the first one. And then it will always go to all of them. Okay? So this is progress. So you have safety and life. So this is a general thing, but this is not a course on proofs, okay? Or else I could give a whole lecture on this. Hopefully you've seen some proofs. We do a little bit of reasoning in this course, but it's mostly about the concepts, the paradigms, and how to use them, okay? Okay, so that's good, huh? Now, I'm going to talk about locks, which is the first one, the first abstraction. Locks are the easiest thing, and it's very intuitive. It's a language concept. You see it in the program language. Only one thread will be running in a specific part of the program. So you have a part of the program, and it's protected by a lock. And you're guaranteed that inside there will be only one thread at most, or 0, but never 2. That means, from the viewpoint of the programmer, it's atomic. The scheduler, when it's inside, all the scheduler can do is make the thread go to sleep and wake it up again. But it cannot choose between two threads, okay? So that makes it atomic, in fact, if you do that. That makes the execution atomic, okay? If another thread tries to go into that part of the program, there's a boundary, and the lock will stop that thread and force it to suspend, to wait until the other thread leaves. So it's really enforced. You can try to get in, but you can't get in unless you're the only one, okay? So here's an example that's something that people sometimes don't understand. So this is a code, let's say it's a bunch of lines of code, and here's a piece of code protected by a lock. Lock L. But actually lock L protects more than just this. It protects both of these pieces. They don't have to be together. They can be separate in the code, okay? This is something people sometimes don't understand. It does not have to be contiguous. So the lock L will protect this. So if there's one thread here, then no other thread can enter, even in the second part, because both of them together, you will have maximum one thread, okay? So this is called the critical section. The part that's protected is called a critical section. That's a standard terminology, and it doesn't have to be continuous. This is then building a big atomic action, okay? Okay, so that's sort of the idea. And the language provides an abstraction. Languages that have locks will often give you an abstraction, okay? It will give you a way to create locks and use them. Here's a simple abstraction. This is the one that's in Oz, but every language has their own little variations. You have a function called newLock, which creates a newLock L. You can also test whether something is a lock. This is because Oz is dynamically typed. You can test whether L is a lock. You can store locks inside of data structures, and they're just like pieces of data. And then you can protect. You can do lock L, and then this is a statement. Guard the statement with a lock. And you can have multiple, you can call this many times. You can do lock L statement 1, lock L statement 2, lock L statement 3, and all of them are protected by that one lock, okay? That means if there's a thread inside here, and another thread tries to get in, it stops automatically. And it waits until the first thread leaves, okay? So that's very nice, huh? That's a nice abstraction, okay? So a thread will wait, or be suspended. That means the scheduler will never choose it. In fact, the lock talking to the scheduler. The lock ensures that the scheduler will never choose it if it tries to enter a guarded statement if there's another thread inside, okay? And then there's a funny thing, which I'll show an example. If a thread is inside here, and if in there you will execute again lock L, like recursively, it's allowed to enter again, because it's already in fact. If you're inside the lock, you can go inside again. The lock statement can be nested. This might seem weird, but it happens a lot. In real abstractions, it's very common that when you go inside a lock, and this piece of code can do a lot of things. You can call, and you might call lock L again in here, and if the thread is in, it can go in again. It can enter again, okay? This is called reentrancy. This is why the locks have to be reentrant. If the lock does not allow that, then it's a simple lock. And actually it's much less useful. If you really want good locks, the good locks are the reentrant ones. And we'll show you how to do both kinds. Okay, so that's how the abstraction works. And I'm going to give you an example now of this. I'll give you an example using a concurrent queue, and we're going to implement it with locks. This actually is the same queue we saw before in the advanced algorithms, but now I'm making it concurrent. But let me make a picture of how the queue works. So if you didn't understand really well how it works, hopefully you'll understand it now with the picture, okay? So a queue has a sequence of elements with a back and a front. So here I have A, B, C in there, and there's two operations. You can do insert and you can do delete, okay? Now let's make a concurrent queue, which means you can call it from multiple threads, okay? And it will be correct. You can have one thread insert and another thread delete, and if you have many threads inserting, many threads deleting, automatically the queue will be doing it right, okay? So this is sometimes useful. For example, if I have print jobs going to different printers, you put them in the queue, each program that wants to print will put it in the queue, and then each printer that needs to print something will take it out of the queue, and it's concurrent. So the queue will do that right, okay? So insert X adds X to the back, and delete X removes an element from the front and binds it to X. So X is an output. So the D here is added to the back, A, B, C, D, and delete X will remove the front, so X will be A. Okay, so that's very simple, right? But we want to make it concurrent now, okay? But I will first show you the implementation, the data, and this is the same as we saw before. This is using difference list, so the queue will be represented as a tuple here, internally, NQ, NFB. N is the number of elements, 3 here, okay? F is a difference list with a tail B. So FB is representing a list, A, B, C, B, and then B is the end. So remember, difference list is representing a list as 2 things, and it allows removing from the front and adding to the end in constant time. That's the advantage, huh? So both insert and delete will be done in constant time, okay? And this one is ephemeral, huh? That means there's only one version of the queue. Only one version, okay? That means you cannot do 2 inserts on the same queue and get different queues, huh? Okay, you will have only one version at all times. But this is okay for concurrency. All of these concurrent threads will be updating the single version of the queue, okay? We're going to store this queue. This is going to be stored in a cell now. Remember in the previous implementation we did many weeks ago, there was no cells. And when you insert a queue, you get a new queue, okay? So that new queue can be used further for inserts and so on, huh? Remember how it worked before? So something like Q1 is equal to insert a Q0. This is how we did it before. This was like function. This is a purely functional thing. But now, since we're using cells, okay, we don't see explicitly this. We're going to modify the queue itself. So we don't actually have an output. So it's not a function anymore. Okay? When you insert D, you will actually update the same queue. So it'll automatically be ephemeral in a sense. There's automatically only one version here. If you use cells, you basically, most of the data structures are automatically ephemeral. It's very hard to make them persistent. You have to do a lot of work. Whereas we showed you in the previous lecture, with functional programming, you can make them persistent in a much easier way. But with cells, they will automatically be ephemeral, okay? So you see how it works, right? So we have to implement insert and delete. This thing, this tuple is stored in a cell. And of course, we do operations on the cell. So all these operations will be inside a lock, okay? Right? You see it, huh? So here is the code for this, okay? So this is a function returning a new queue. So this returns a record which actually gives you the insert and delete operations, okay? Insert and delete are procedures which have the X argument. But the cell is hidden inside, huh? There's a cell here. The initial value is 0xx, that's an empty Q, huh? XX is an empty difference list, and 0 is the number of elements, and L is a lock. So you have a cell and a lock, okay? And now we define insert and delete. And here's how you define them, okay? And if you look at the functional code we did before, you can actually see, compare the code. It's actually a good idea. So here I do insert X. So all of the code is inside the lock, okay? And the same for delete, huh? And I will read the cell, and I will update the cell. So I do a read and an update, okay? Now, this is two cell operations. And I don't want the scheduler to stop in the middle because the queue would be inconsistent. And then I would be, if I do two inserts, for example, and if there's no lock, then they will both start with the same queue and it will be buggy, okay? So this has to be atomic. So the lock will make it atomic, okay? So I will here read the queue. So I get N, F, and X, B. So I bind X and B2 to the tail, and the new queue will be the difference list FB2. This will be the queue with the X added into it. And the number of elements is X plus N plus 1, okay? And the delete is kind of symmetric. So the delete has to bind X, So I get the O value. So this one is actually bound to the content. So N will be the number of elements. X is bound to the first element. F2 is bound to the rest. This one will, if it's ABC, this will be A, this will be BC. And then the result is N minus 1, and F2 is just the rest, B. So this is a queue with one less element, okay? But these two again have to be atomic. So this insert and delete, you can call it for multiple threads, and there's no problem whatsoever, okay? So you see, it's not so hard actually. You just use locks at the abstraction boundaries. So that internally to the abstraction, you're free to do many operations on the cells, okay? So that actually is easy. That actually is, in many cases, this is very easy to do, okay? But not always. Sometimes the threads have to collaborate. In the queue, the insert and delete, they never have to wait. So this is easy, you can see it. But there's examples where it's much harder. And the typical example is a bounded buffer, where if I put an element in the buffer, or if the buffer is full, then I have to wait until somebody else takes an element out. Okay? So in deterministic data flow, this was done where the producer waits until the consumer takes an element out, and then the producer can go forward. But we can do bounded buffer also in shared state. And then we have two threads. One thread putting elements in, and another thread taking elements out. But it's not so easy as this, because the threads have to work together. If the buffer is full, then the put thread has to wait until the get thread takes an element out. Whereas in this case, the threads never wait. There's no waiting here, right? It's always possible to do insert and delete here, okay? So many data structures are not so simple as the queue. Many data structures are like bounded buffer. They fill up, and then you have to wait until it goes empty again. So you have to collaborate between threads. And that's actually where you need monitors. So locks will not be enough for doing a bounded buffer, okay? So I just mentioned that now, but we'll see that really next week. It's just to prime you a little bit on that. So this is not solving all the problems, okay? It's nice, but it's not solving all the problems. And now, let me just give you one thing before we make a break. Why does the lock have to be reentrant? Now I can actually show you. Why does the lock have to be reentrant? That means if I'm in the lock, and if I go in again, I should be able to do it. So naively, whenever I do lock and there's a thread in there, I have to block. Even if it's the same thread that's already in, I have to block. That's kind of simple, too naive. So reentrant means that if I'm in the lock and I do lock again, I have to be allowed to go in again. So why do we need that? Here is a simple example. Let's extend our queue abstraction. Let me define a new operation in the queue called insert2. And insert2 will insert two elements in the queue. A, B, boom, boom. Okay? But nothing in between. The two are next to each other in the queue. It's like two people waiting in line and nobody cuts in between them. Okay? So we do this. Insert 2xy, insert x, insert y. But this will not work. Because the scheduler, of course, can put other things in between there, between the two inserts. So how do we guarantee that no thread comes in between? We have to use a lock, okay? So the way to do it is by doing lock L. And then we make sure that only one thread, but inside of the insert there's already a lock. There's already a lock in there and in there. But for reentrant lock, it's not a problem. You see that? When we call insert X, the thread is already inside, okay? That means the lock is reentrant. It has to be reentrant. Reentrant means I go in here, but then when I start executing insert, there's another lock in there, but I'm already in. So I'm allowed to go in multiple times, okay, since I'm already in, okay? So that's logical, and that's how reentrant threads work. And then when I leave, though, when I leave the lock here, I'm still actually in, okay, because I'm still in this big one. So that means that when I actually leave the lock inside of insert, I'm actually not going out yet. Because I have to go out, each time I go in, I have to go out the same number of times to be really out. So after I leave the insert, I'm still in, okay? And again in the second insert, I go in again and then out. And then here at this end, I'm really going out. Okay? So you see how it works? It's clear? Okay, so this is how reentrant locks work. Okay? So let me now make a small break. And after that, we're going to implement the locks. I'm going to show you how to build them so you will become true masters of the locks. Before I implement locks, I want to show you something interesting, okay, about the queues we did. This queue here. This queue with difference lists, actually, it's able to do something that is very, very nice. The queue I showed you, you are able to delete elements before they are inserted. The delete never waits. That means if the queue is empty, it's empty, there's nothing there. And then you delete, what happens? Well, if you do that, you will return an unbound variable, and the number of elements in the queue will be -1. How does that work? How does that make sense? Well, it means the next time you do an insert, that will be the X. So that means that the next element inserted will be the one that you deleted. That means there's no constraint really on the order of delete and insert. That works because of single assignment variables. You can see it's actually a very powerful concept. I have shown you many advantages of this already for deterministic data flow, but here you can see another interesting use. Okay? You can actually delete elements from an empty queue. It's like you borrow the elements, and then later when you insert, that those will be, it's correct, they will be bound to the ones you've deleted, okay? How does this work? I'm not going to show you how this magic works. If you want to see how it works, try running delete on an empty queue and see what happens to the F and B variables. it works. Okay, and do an insert. So that means it's completely free. If I do delete and insert, I can change the order and the result is the same. Okay. Now, sometimes you don't want that. Huh? If you want the queue to block when it's empty, you have to do that yourself. That means you have to call a wait. If I want to block when I try to delete from an empty queue, I have to wait explicitly. So the wait X will wait until X is bound, until someone inserts. Okay? But if you don't do that, the default behavior is that the insert and the delete will always work and never block. And it's correct. This is because of the way single assignment and difference lists work. In fact, there's nothing special about queues with negative elements. It's just that the elements, they will, when you insert them, then they get bound to what you insert. So you have, it's like you borrow from a bank. Huh? You can borrow money from a bank. So if I have, I can borrow money, and the bank has negative money, okay? And I have money then, or something. This works. Governments do this all the time, okay? Negative money is not a problem. But here you also have negative elements in a queue. Huh? So this is just something I wanted to attract your attention, that single assignment is actually a very good and powerful concept. We saw it in deterministic data flow, and it should be general in many, many systems. It should be used everywhere, but it's not yet. It might in the future, okay? There is a language called Prolog Logic programming, which does that, but Prolog is kind of a niche language. It's not really mainstream, even though there are very good systems using Prolog. Huh? So if you want to really see the advantage of single assignment, you should look at this Prolog language, okay? But I'm not going to say more about that, just to tell you that this is a very nice thing, and it should be everywhere. Deterministic data flow should be everywhere. It's not yet, but maybe in 10 years it will be, okay? Okay, I want to show you another thing with queues. So if you're kind of alert, you will notice that, in fact, we can do the queues using exchange, okay? We don't really need locks in this particular queue, because an exchange x, y is the same as reading x and binding the new content to y. So you can do the insert and the delete using exchange, okay? Notice the n plus 1 and the minus 1 has to be done after, because when you do this arithmetic operation, the n has to be bound. So I cannot put n minus 1 inside the argument here, because I don't know the n yet, and that means it will block. So I first have to read the n, and then later I can do the n minus 1. So the arithmetic, the n plus and the minus 1 has to be done after. If you don't do that, it won't work. So this is a very simple example. But still, if you want to do insert 2, you will need a lock, of course, huh? Because insert 2 does 2 things, and exchange only does 1 update. You can see exchange as kind of doing an update, replacing old value by new value, so it's like an update. But if you do more than 1 update, or if I'm updating many things, in a database you will typically update many things. Later, when we see transactions, you will usually have many things to update. Like in a bank, when you transfer money from one account to another, you have to decrease the amount in one account and increase in the other. That's already 2 operations. But you have to also keep track of this. You have to keep an audit, a log, a trail, so that later on, if there's some kind of a legal investigation, you have to have another cell that remembers the set operations that were done. So that's already a 3rd operation. And maybe it costs money to do that. So you have to update a fourth account where you're paying what it costs to do the transfer. You see, already we have 4 updates for a simple transaction. So there you absolutely need locks. In this simple example, where you only have 1 update, you can do it as exchange. But as soon as you need more than 1, exchange doesn't work. Exchange is a primitive. It's a primitive. It's not enough for everything. You need, when you combine the exchanges, you still need locks. Okay. Okay, so that's all I'm going to say about the queues. Now I want to implement locks. Okay, I want to show you how to build the locks. We are going to implement locks, and internally, a lock, we will implement it using cells and exchange. So the lock really, really depends on exchange to make it work. And I will do it in 3 steps. The first, the simplest one, I have to do a very simple lock first, which is not reentrant, the simplest one. And then the second step, I have to add something because of exceptions. Okay, so exceptions have nothing to do with locks, but it's possible that inside of a lock, you raise an exception. And the exception will go to the exception handler. It's possible because we have exceptions in the language. And when you leave, so the exception handler, when you raise an exception, will leave the lock. So you have to, the lock has to know that. The lock has to know when you're leaving, even with exceptions. That means you have to do something there. So this, I will show you how to do a simple lock that handles correctly the exceptions. And then finally, I show you how reentrant locks work. Okay? So the main idea is the first one. The first one, the simple lock, really shows you the idea. And the idea is called token passing. This is a very powerful technique. It's used a lot, everywhere, okay, in many, many systems. And so this is an example of that technique, okay? So token passing is a technique that's used in concurrent and distributed program a lot. And it's based on a concept called a token, in French, un jeton. And there's only 1 token in the system. Actually, there's only 1 token for each lock. Each lock has its own token, okay? And the thread that's in the lock possesses the token. And if a thread tries to get in without the token, it cannot get in. So the token is what gives you the right to get in, okay? So this is how it works. And when a thread leaves the critical section, when it exits the lock, it gives the token to the next thread that's waiting, okay, to get in. So that way we can be sure there's always only 1 thread because there's only 1 token, okay? So this is the idea how it works. That you have a bunch of threads trying to get in the lock, but the only one that's in is the one that has the token. And when it leaves, it gives the token to the next one, and so on. So this is how it works. Okay? This is the idea of how you guarantee that there's only 1 thread. So now let me show you the code for this, how this works. Okay? This is a simple lock. When I call function simple lock, it will return a simple lock. Okay? And it basically returns a procedure lock. Okay, this is so it's using high order here, right? Because I want to protect any statement. I want to lock this statement. Okay. So the P argument is actually a 0 argument procedure that represents any statement. And in the real system, the lock L syntax is just syntactic sugar for this, okay? So any language that has a lock, the statement is actually a higher order thing, huh? It's a 0 argument procedure. So the actual lock is here, and the statement is P, okay? And there's one cell, and the cell represents the token. Okay? So how does it work? Well, a thread that tries to get in, it will have a variable. Here it's called old. In fact, the thread that tries to get in the lock has a variable that says whether it has the token. So this variable old will be bound if the thread has the token, and otherwise it will be unbound. Okay? So this one here, if the thread tries to get in, and it's the first one, so unit is a constant, okay? It starts with lowercase, it's a constant. So the first thread that tries to get in, old will be bound to unit. So that means I have the token. So the first thread can get in. But there's a new variable now, which is unbound. So if the second thread tries to get in now, and the first one is still inside, the second one will get an unbound variable. Okay? And it will wait, because I have here a wait. Okay? And when the first thread now leaves, it will bind new. Now notice, the new variable from the first thread is the same as the old variable from the second thread. So let me maybe make a picture to make it really clear how it's happening. Luckily, I have some space underneath to make a picture. Okay. So here I have thread T1, okay, and it has two variables, old and new. Okay. And I have a thread T2, old and new. Let me call this one old 1, new 1, old 2, new 2, and maybe I have a thread T3, old 3, new 3. Okay? These three threads are trying to get in the lock. So we're assuming that T1 first is the first thread that tries to get in. But notice that the old is actually the value of the cell token. So old 1 will be equal to unit, which is a constant. Okay? It could be anything. It could be 1, 2, 3. I say unit here because it's just a constant. I don't care what the value is. So T1 and new 1 is actually the same as old 2. Because the thread T1 will now update the cell, and the content of the cell is now new 1. And now when the second thread tries to get in, it gets the content of the cell, which is old 2, but which is the same variable as new 1. Okay, so these will always be the same, okay, like this. And notice old, this is unbound, so it does a wait here, wait of old 2. Okay? So T2 cannot get in because it does not have the token. Now when T1 goes out, when it leaves, it will bind new. So new 1 is equal to unit, but that actually binds old 2. So that lets the second thread go in. You see? So this is passing the token to the second thread. Now, so the second thread will now go in. But assume now there's a third thread that tries to get in. It will do a wait on old 3, and it will wait. But once the second thread leaves, it will do new 2 equal unit, and this will cause the third thread to go in. You see, so the threads are connected like that. The new variable of each thread is always the same as the old of the next thread. And it goes on for as many threads as are trying to get in. So here's T4, and so on. So passing the token, so this binding is passing the token, it's forwarding the token. And the wait is waiting for the token. And the previous thread will pass the token when it leaves, okay, and then the next one will go in. So notice, if you do this, if you're inside of P, the only way to be in there is if you have the token. And only one thread can have the token, because any other thread that tries to get in will wait. And they will wait in a line. So if many, many threads try to get in, 1,000,000 or 1,000 threads, this will create 1,000 suspended threads. And there will be a whole queue of threads here, in fact, waiting. And they will all be connected. Each thread has a link to the thread before, okay? T2 has a link to T1, T3 has a link to T2, and so on, huh? Let me maybe make lines here to make sure that you can see that they're not, so this is all T1 stuff, left of the orange line. Between these two lines it's T2 stuff, and so on, huh? And the only connection between the thread and the next one is that the new of one thread is the same as the old of the next one. And that's because of the exchange, huh? The old is the value of the cell, and the new is the updated value. And the next guy doing an exchange will get the old value, which is, so the old will be the new from the previous one, you see? So it's because we're doing these exchanges that we have this sequence. So you automatically have kind of a queue of waiting threads here, okay? So it's important. So this is important to understand how this works, huh? So the wait is like the gateway. You're waiting for the token, and the new is when you leave, is to forward the token to the next guy. And if there's no next thread, that's okay. The cell will be unit, and then later on, when a thread tries to get in, it will get in right away, immediately. Okay? So this is token passing. Notice this is using single assignment data flow. So you can see it's very powerful. It's only a few lines of code. Huh? If you want to do this using more complicated, a language which has no single assignment, it's more complicated. Because you have to have a representation for the token. Here, the token is just whether the variable is bound or not. And each time the cell tries to get in, it actually creates another new variable. Huh? It creates another one. And the old is bound to the previous one. Huh? You see how that works? So this is important. Huh? And P can be any statement because of the higher order. Huh? So you see, you don't really, this can also work without higher order, but the higher order makes it extremely generic. Huh? You can put in really any statement you want here, and it will work. Okay? It will work. So we're actually using higher order, cells, and exchange to define and data flow variables. And that lets us define the simple logs like this. Okay? So you see how that works? Is it clear how it's working? This is important to understand. So you should make like a diagram to really understand it. Now we have to make this more practical. So this one is not reentrant. If inside of P you have another call of lock, so let me make a diagram here. So the P can be any statement here. The P here is any statement, and it can be anything. Inside there could be another lock with another statement. So statement 2. So inside of statement, you could have, again, a call to lock. Of course, there's nothing preventing this thing from being recursive, okay? Inside of P, you can have another call to lock. So what will it do? What will this one do? So this guy is running, and when it goes here, it sees, so T1 is running, let's say, it's in here, and it will wait. It's kind of naive. It will wait until T1 goes out. So this one will actually wait, but it will wait forever. So this will actually not work very well in the simple lock. You see, when I'm in the lock and I try to go in again, I see, oh, there's already somebody in, I have to wait. But it's actually me who's already in, you see? But it waits anyway. It doesn't recognize that it's the same guy who's in. Huh? So the lock sees that somebody else is already in. The T2 is the same as T1. And so it waits. So the thing actually deadlocks. That means the whole system blocks. So it's buggy. Huh? So this does not work in the case. If you try to use it in reentrant fashion, it will not work. You see that? Because each time you do a lock, you don't care who's in. As long as somebody is in, you wait. But if it's you that's in, then you wait until you go out. But since you're waiting there, you will never go out. Because to go out, you have to go to the end. Huh? That means the thing blocks forever. So this does not work in a reentrant fashion. Okay? You see that? If you try to use it in reentrant fashion, the system will simply block forever. Okay. So we'll have to do something about that, but we'll do that in a few minutes. It also has a problem with exceptions. If inside of P, if you raise an exception, then you do not execute new as unit. You immediately go to the exception handler. Okay, you remove all execution from the stack until you go to the top, to the exception handler that was created in the try statement. So you will not actually leave. So that's not good. You want to leave always, even if you raise an exception. So we have to fix that. But luckily, the fix for exception is actually very easy. Okay, here's the fix for exceptions. We actually put a try finally. There's an exception handling. The try finally will always execute this, even in the normal execution or in the exception. Okay? That means we need to execute this because we leave the lock. That means if P raises an exception, you will also leave the lock. Because otherwise, if you raise an exception, you stay inside forever. That's not good. Okay? That's buggy. You have to remove it. So your language has exceptions. So if the statement raises an exception, you still need to pass the token. Okay? We can fix this by putting a try finally here. And then it works with exceptions. Okay? That's nice, huh? But it's still not reentrant. Shit, the reentrant is the one we really want here. Huh? So how do we make this thing reentrant? Well, we have to be very careful now when we go in. When you try to go in, you have to check first whether you are already in. And if you are, you don't do all this token stuff. If you're already in, if T1 is already in, it does not have to do any kind of token passing whatsoever. So you actually have to add a check here at the boundary whether you're already in. And if you are, you just keep going. You forget about the token. So it's actually not that hard if you understand how it works. You just don't have to do any token stuff if you're already in the lock. So here's the code for the reentrant lock. Okay. So we're changing the lock procedure here. We have to add a new thread, a new cell, sorry, current thread. This tells me which is the thread that's in the lock right now. So we have to know who was in there, because I have to see whether I'm the same as the guy that's already in, okay? So we need another cell that tells me who is in, and we need a new concept. We need identity of the thread. Every thread has to have like a name, like this is thread George, this is thread Bob, this is thread Ronald. So the threads need names, okay? So that's an extra concept. You can only do reentrant locks if the threads, you can actually give them like special little names. And in Oz, there's a function called thread.this, 0 argument, and it returns the identity, so the name of the thread. But this can be a very easy thing, huh? In a language like Java, internally, a thread can have a slot in the internal thread data structure which gives the name of the thread. Huh? So the thread needs an identity, a name. So then the lock works like this. So you still have the part where you're doing the token stuff, but sometimes you don't need to do it. If thread.this is equal to the current thread, that means if I am the thread that's already in, current thread is the one that's already in, then I immediately P. So I don't have to do any token stuff if I'm already in the lock. And I do that with a simple check. Otherwise, else I have to do, if some other thread is in, then I have to do all the usual token stuff, okay? Notice I have to update the value of this current thread, So wait old will go in, but once I go in, I have to update the current thread. Current thread is : equal thread this. And when I leave, current thread is unit. Unit means there's no thread inside. So when I have to add some assignments to update the current thread value. To know when I'm running P, at that point, current thread will be the identity of the thread that's in. So if inside this P, I run another lock recursively, then I will not do any token stuff and I will just immediately do the body. So this is actually a kind of a subtle concurrent program. So we started from token passing using wait and new, using exchange. Then we add the try finally for handling exceptions. And then we had this test to avoid the lock stuff when we're already in, okay? So this is a reentrant lock. So this is a complete and correct definition of a reentrant lock. And all systems that have locks will do it like this. It might not be implemented exactly in the same way, but it has exactly the same behavior. So this is really how reentrant locks work, okay? Now, I want to give you some exercises on this, okay? So this is a concurrent programming, and it's really important to understand how this works. And the order is very important here. So first you do exchange, then you do wait, then you do current, then you do P, then you assign current, then you do new. The order is super important here. If you change that order, it's buggy, okay? So I want you to do exercise. 2 exercises. I want you to think. So here we have the body of the token passing. We have the wait, we bind current thread, we run P, we bind current thread to unit, and then we bind, so here we update current thread, and we bind new to unit to pass the token. So wait old enters the critical section, so it's right at this point, and new equal unit leaves. So everything inside this red part, it's all critical section, okay? And then we update the current thread before running P. That means inside of P, current thread has a correct value, okay? And after P is done, then we have to do some cleanup. There's no more threads, so current thread is unit, and we pass the token, okay? So I want to ask you 2 questions now. What can go wrong if I switch these 2 instructions? Why? Show me a scenario of the scheduler that gives a bug. That means I first bind current thread, and then I do wait old. Okay, if I switch those 2, what can go wrong? So that's one question, and I'll give you some hints. And another question is, what can go wrong if you switch these 2? Okay. If I do new equal unit, and then I update current thread after that. If I switch these 2, or these 2, each way, then it's buggy. The whole system is buggy, okay? And let me give you some hints on that, because that's actually debugging concurrent program. It's very hard. Have you followed already the program by the course by Shared-State Méthode de construction. So you have some idea that it's hard, huh? Debugging concurrent programs. So here, what happens if I switch these two? That means I first do current thread is equal to thread this, and then I do wait old. I do it in this order, okay? So I'm switching these two. So what can go wrong now? So you have to imagine what this means, okay? This means I'm assigning the current thread before I wait, right? Okay? It means maybe there's already another thread inside the critical section, okay? And I have to wait. Maybe I cannot go in yet. Maybe there's already another thread in there. But if I assign current thread to me, thread this, that's me, then that other thread will no longer be able to do reentrancy. You see that? Because I'm interfering with the other thread. You see what's going on? If the other thread now has to go into lock again, it thinks that it's me that's in there because of this, and not that other thread itself. So it will block. So the system will go into a deadlock if I do this. You see that? Okay, so I say that very quickly. If you don't understand it completely, look at the video again, okay? And try to figure it out. Think about it a little bit. It's very important to understand this, the ordering, huh? So let me give you now some hint on the other one. Let's say I do new is equal to unit, and I do current thread. I update it, so that's a cell, to unit. I do in this order. So I've switched these two. So what does that mean? It means when I do new equal unit, I'm leaving the critical section, okay? I've left already. So when I reach this point, in between those two, I'm out. But the current thread is still me, okay? It's still the value of me, okay? In there. So this is a little bit more subtle. The current thread is still me. Now what happens if another thread tries to get into the critical section? A different thread. Now the scheduler, let's say, has put me to sleep here. It's allowed to do that. Huh? So in debugging a concurrent program, you have to imagine that the scheduler is a nasty guy and is doing exactly the wrong things. So the scheduler here is putting this thread to sleep in between these two instructions. It's perfectly allowed to do that, okay? If another thread now tries to get in, that other thread will get in, okay? It will get in because it will have a different thread ID than this one. So that seems to be okay, right? If another thread now tries to get in while this one is sleeping, and this one is out now, after the new unit, I'm out. Another tries to get in, it will get in. So that seems to be okay, yeah? But now, what happens now? Do you see now what can happen? What can happen now? So that other thread it's in, everything seems to be happy. English is say it's hunky-dory, that means everything's okay, the sun is shining, and so on. But then the scheduler, the nasty guy, wakes up this thread and executes this. And so the other thread that's in has now its current thread variable set to unit and not to itself. That means if that other thread now tries to do reentrancy, it will block forever. So if the other thread tries to go in again, it will have a deadlock, okay? So that's a little bit more subtle than the previous one, huh? So what do you think? You get some idea of how to do it? If you don't understand completely how to do these, then think about it. It's very important. One of the things in this course that I ask you to understand is I ask you to understand how concurrent programs work. And concurrent programs, the scheduler can do anything, okay? And sometimes and you cannot assume the scheduler is doing nice things all the time. You have to assume the scheduler is a bad guy and is doing exactly the thing that makes your program break, okay? Because it will happen. It will happen when you run your system millions of times. So both of these, if you switch these two, or if you switch to, both of them cause bugs, okay? So I'm going to ask you, so I've given you a lot of hints, I've even kind of explained it, but you have to understand this. I can give you a concurrent program, a simple one, on the exam, with a small bug, and I can ask you, why is it buggy, okay? And you have to imagine that the scheduler is doing exactly the thing that makes the bug show up, okay? And that it's not nice. You have to, schedulers are not supposed to be nice guys, okay? Scheduler can do whatever it wants, within the limits of fairness, but here I'm not breaking fairness at all. The scheduler can put this one to sleep for a little while, it's not breaking the fairness, and then wake it up later, fine, okay? So I'm not even breaking fairness or anything. The scheduler is allowed to do that. Okay? Okay, so now I want to show you more things, but today maybe I will stop for today. I will now show you another concept, which is actually a more sophisticated form of shared memory, of shared state concurrency, called Tuple Space. So this one is actually pretty nice, and it's kind of halfway in between shared state and message passing. So it's interesting to see that, so that you can understand the connection between shared state and message passing. So this one I will show you next week, Tuple spaces, and then we'll go into monitors, and then I'll show you monitors. Okay, so let me stop here for today. So make sure you understand how the reentrant lock works, Okay, so that's it for today. Thank you.